Given the chiral nature of amino acids and peptides in biological systems, there are various reasons why separation of differing chiral compounds can be necessary. Whether for pharmacological, industrial, or analytical purposes, HPLC can be an effective method for separating these compounds. Enantiomeric amino acids will elute alongside their mirror. However, through derivatization with Marfey's reagent, separation can be achieved. In this video, we will be going over how to prepare your standards and samples for analysis with HPLC using this method. To give a brief overview, this video will be covering the materials and equipment required, how to prepare the reagents, standards, and eluents we will need, the procedure for derivatizing a standard sample with Marfey's, and a few other considerations which may help smooth the process. Let's begin with what we'll need. PPE such as gloves, goggles, and a lab coat, Eppendorf pipettes and matching tips with graduated cylinders, plastic vials for derivatization and standard storage as well as HPLC vials and caps, chem-safe bottles and caps as we'll be working with strong acids, syringes with filters, a heating mantle which the plastic vials will fit into, sodium bicarbonate and hydrochloric acid. We will use 6 molar hydrochloric if you follow the provided measurements. We will also need acetonitrile as our eluent, acetone for dissolving the Marfey's, acetic acid and formic acid, our derivatization reagent Marfey's, and amino acid standards depending on our analyte of interest. With these ready, we can begin. Our mobile phase is up first. As this analysis requires a gradient, we will have an A phase and B phase eluent. Our B phase will be 100% acetonitrile, while our A phase is 10% acetonitrile and 90% ultrapure water. Acetic acid will be added to both to enhance separation and avoid ionization. The ACN bottle is rather large, so best to be safe using a transfer beaker. Add it until the meniscus reaches the measured line and pour it into the HPLC's eluent bottle slowly. We only need 500 microliters of acetic acid for both, so our Eppendorfs will be handy here. Once both are made, these bottles can be connected to the HPLC pumps. Sodium bicarbonate will be added to deprotonate the amines and make them stronger nucleophiles. We will be making a 1 molar solution dissolving 2.1 milligrams into 25 milliliters UPW. We'll start with the water, as starting powder first can leave you with a sodium bicarb clump that will take a lot of mixing time to dissolve. Giving your whey paper a soft crease can help with transferring your powder into the vial. The powder is rather cakey, so it may fight you when trying to weigh it or add it to the plastic vial. Make sure to mix it well with each use as it tends to settle. We can store it in the freezer until needed. Next, we will be preparing our hydrochloric acid, which is used to neutralize our samples after derivatization and quench the reaction. We're using 6 molar hydrochloric and we'll be adding it to a chem-safe bottle. Start by adding 5 milliliters of ultrapure water to the bottle, as adding water to the acid will generate heat and it's best to be safe. Then we add our acid. For 1.65 milliliters, we will use our pipettes with a fresh tip. Fill with water up to 10 milliliters and give the bottle a gentle mix. Be sure to store your acid where it's appropriate. Our samples will need to be diluted after derivatization, so we will be making a water and acetonitrile mixture for this. We'll begin by adding our 10 milliliters of acetonitrile to a clean chem-safe bottle. Follow this by adding 90 milliliters of ultrapure water to the bottle. You can add the acetonitrile to the glass using the pipettes, but I don't recommend adding 90 milliliters of water, 1,000 microliters at a time. With the larger grad cylinder, pour your water carefully to avoid losing volume, as we want to make our reagents consistent each time. We'll add our formic acid using a pipette and fresh tip to lower the pH for our separation. Mix your bottle and store it in the fridge for future use. We will need a set of standard amino acid solutions of our target analyte, enantiomers, and similar elution time amino acids to generate our standard curve for identification and quantification. To make our 50 millimolar stock solution, we'll begin by adding water to the plastic vial for the same reason we did the bicarb. Some amino acids will be more trouble to dissolve than even it was. Weigh out your amino acid and add it to the vial. Don't worry about camera angles when you're adding your amino acid, just be sure all the weight analyte makes it in. Make sure to mix it well, just as with the sodium bicarbonate. These standards can be frozen until needed as well. Our HPLC labeling reagent Marfey's will need to be dissolved into solution, so we will be using 99% water and 1% acetone. It can give issues with dissolving, so the acetone can be increased up to 10% to ensure it fully dissolves. We will begin by adding the water to our glass bottle. You'll need both a grad cylinder and pipette for our measurements. Acetone tends to evaporate rapidly even within the pipette tip, so be swift when adding it or it will drip out onto the counter. The reagent tends to clump up and stick to everything, so I recommend adding it towards the edge of the whey paper and be careful when adding it into the bottle. Definitely don't worry about camera angles for this one. It can take some time to get the Marfey's to dissolve, especially if it was very cakey. We don't want undissolved particles in our reagent. So make sure it's mixed well and remixed before use. The reagent is stable, however it will degrade in light. Be sure to cover it to minimize this and store it in the refrigerator until needed. With our reagent standards and mobile phases prepared, we can now move on to the derivatization process. We will be preparing our standards according to this chart, depending on our desired concentration. Bring your frozen standards out and give them plenty of time to defrost. We want them to be room temperature when we begin aliquoting. They will need remixing once defrosted, and depending on the size of your vial, this may take some time. One way to decrease how long is spent watching ice melt, we can aliquot the standards ahead of time into the derivatization vials, as well as add the sodium bicarbonate. When dispensing, touch the pipette to the wall of the vial to ensure any residual is dispensed. These smaller vials can be frozen and defrosted much faster than our larger vials. While they defrost, we can also get our heating mantle up to temperature. Make sure your other reagents come to room temperature as well. With our samples defrosted, we can now aliquot the standards, sodium bicarbonate, and Marfey's, or if they were prepared beforehand, just add the remixed Marfey's. With our Marfey's added, they will need to be mixed at least 4 minutes. A vortexer comes in handy unless you want sore forearms. Once the heating mantle reaches temp and our samples are mixed, place them into the mantle and allow them to cook for 1 hour. An hour is a long time, so while those derivatize, let's cover some factors which may affect our elution. For amino acids like histidine, ornithine, and lysine, multiple peaks may be resolved for each enantiomer, as the Marfey's can interact with both amine groups. We will get peaks for monosubstituted forms for each amine group, as well as disubstituted forms. We can push the equilibrium towards disubstitution by using a greater excess of Marfey's reagent when analyzing these. Tyrosine does not have multiple amine groups, however its hydroxyl group can interact with Marfey's reagent. By raising the pH of our solution during derivatization, we can push the equilibrium towards the disubstituted form. Our samples are still cooking, so we can get the last steps prepared ahead of time as well. We need labeled HPLC vials for each of our samples. Be sure they are clearly labeled so you know which sample is which when adding to the vials and placing into the HPLC. We will also need syringes with filters for each samples, so these can be prepared ahead of time as well. Removing the plungers ahead of time will keep you from having to fight with them while your samples are in your workspace. Your HPLC will need purging and equilibration before your run, so now is a good time to get those started. With our samples done derivatizing, we are left with pale yellow samples, or deeper yellow depending on concentration and which analyte it is. Allow the samples to reach room temperature, then we can quench the samples with our hydrochloric acid and dilute to the same volume using our acetonitrile solution. We'll need to make sure to mix our vials thoroughly once again. We can now add them to our HPLC vials. We don't want any undissolved particulate getting into the HPLC column, so we will filter our samples with the syringe, adding slowly to make sure the pressure doesn't burst the small filters. Make sure you're in position once you begin placing the plunger back in, as the initial flow may move faster than expected. Once you've capped your HPLC vials, your samples are ready to run. Here's a good 7 hours of separation ready to run. With that, we've covered what is needed, how to prepare our samples, how to derivatize, as well as some potential stumbling blocks to keep in mind. You're all set to begin running with your HPLC.